In this example, what we will do is we will study the natural frequencies and mode shapes using Holzers method. Whatever we have done earlier, we have seen this example earlier, and we will use Holzers method. How to use Holzers method? In this, you take station 2 to the right of this mass, station 1 to the right of this mass, and station 0 near the wall. And you have two springs K1 and K2 and the two masses M1 and M2. So when you connect, let me now relate with the transfer matrix station 1, state at station 1 with that at 0. You know x of R1 will be equal to 1 by K1 minus omega square M1 1 minus omega square M1 by K1. This is the transfer matrix that relates to xf at 0. But we already know the displacement at this point xr0 is 0, and uh, once you do that, you will get x xf r1 will be, when you multiply this 0, you will get 1 over k1 1 minus omega square m1 by k1 times f r0. Now we will consider the transfer matrix between station 2 and station 1. Similarly, the equation that you write is xf r2 will be 1 by k2 minus omega square m2 1 minus omega square m2 by k2 times xf r1, that is the state at this point. But you already know the state state of the system at this point to be 1 over k into 1 minus omega square m1 by k1 times f r0. So when you substitute xf r1 from this, that is from this, in this equation, and we also know that is, as I told you, we need to apply the end conditions. The another end condition that we have is FR2, the force at this point, is 0. So once you substitute FR2 as 0, this equation, that is FR2, once you make this to be 0, then the corresponding equation will be 0 will be equivalent to minus omega square m2 into this plus my 1 minus omega square m2 into F. Okay, this of course is substituted. This matrix you have substituted here. The corresponding equation that you get here is 0 is equal to minus omega square m2 by k1 plus 1 minus omega square m2 by k2 into 1 minus omega square m1 by k1. Well, when you simplify this equation reduces to omega 4 minus omega square into k1 plus k2 by m1 plus k2 by m2 plus k1 k2 by m1 m2 equal to 0. This is the same, as you will notice, this is the same equation as we obtained when you had three springs k1 k2 k3, and in this particular case this is the situation where the spring k3 connected to the wall is made 0. Then you get the reduced equation to be the same thing as this. So applying Holz's method also, you get the same frequency equation. Once you get this frequency equation, next all you need to do next is, knowing the values of k1, k2, m1, and m2, you can solve this equation to obtain the two frequencies omega 1 and omega 2, which are the two natural frequencies corresponding to the system. The next job will be to find the mode shapes. Finding the mode shapes, you need to find out xr1, that is the displacement of mass 1. That is, from the previous matrix we will see this is equivalent to fr0 by k1. I will say this displacement, let me take it as 1, because what we are interested in mode shapes is only the ratio of the amplitudes. Let me take this as 1. Then from the previous equation 3, you will find that xr2 is xr1 plus f1r by k2. Again from equation 1, you would notice that fr1 is equal to fr0 into 1 minus omega square m1 by k1, and so therefore substituting f1 fr1 by this expression, you will find xr2 to be xr1 plus fr0 by k2 and so on. Again, because I have taken xr1 equal to fr0 by k1 both to be equal to 1, this equation will reduce to xr2 is equal to 1 plus 1 times k1 by k2 minus omega square m1 by k2. Therefore, you can get x2, xr2 or x2 for the appropriate natural frequency, whatever you substitute here. you will get XR2 one value for omega 1, another value for omega 2, once you know K1, K2 and M1. Well, so basically if XR1 is 1, XR2 whatever value you get is going to give you the amplitude ratio with respect to X1. Therefore, at both of these frequencies we can draw the mode shapes for the particular problem that we have now considered. Well, now we can look at the problem here. What we have taken is spring mass system. We can handle the rotors with the shafts in the same fashion. The only difference is the state matrix is going to be theta t instead of x and f. The rotary counterpart is theta is the theta and t, and in the place of K, the spring stiffness, you are going to get the torsional stiffness Q, and in the case of in the place of mass of the spring mass system, you are going to get the mass moment of inertia of the rotor. That is the only change. In all these equations, all you need to do is substitute K's by the corresponding Q and masses by the corresponding mass moment of inertia of the rotor. Otherwise, the equations are precisely the same. You can find out the natural frequencies and also the mode shapes in the same way that I had explained earlier. Now let us see how Holzers method is applied for a 3-rotor system. We have worked out the frequencies, natural frequencies and mode shapes of a 3-rotor system earlier by a different method. Here we will see how Holzers method can be applied. The way Holzers method can be applied is basically you name the stations. I take the station at the end of the 3rd rotor as station 3, station 2, station 1. I will also be needing one more station that is to the left of this mass. Basically, the relation between the state here to state here is only going to be a point matrix as you have seen earlier. So once we have this relation, then all I need to do is relate this to this, relate this to this, and I already have some relation, so I can estimate this. That is, same thing I have written here. The state matrix theta t R3 is 1 minus 1 over Q3 minus omega square I3 into 1 minus omega square I3 by Q3 into state matrix at station 2. Similarly, state matrix at station 2 is related to the state matrix at station 1 by this similar equation. Now, what you have here, theta state matrix R1, that is the state at this point, that can be related, as I told you, from the point matrix of this rotor, which is simply 1 0 minus omega square I1 times 1 of theta t to the left. To the left of this rotor, we know the torque to be 0. Anyway, so theta t R1, once you work out, you will find this is 1 minus omega square I1 times theta L1. Now taking theta L1, which is the same thing as theta R1, because basically there is no rotation in this mass, in this rotor to the left and right. So let us take that to be equal to 1, so that we have the state matrix theta t R1 will be simply 1 minus omega square I, well, as demonstrated here. Well, with this, all we have to now do is get theta t R3 by combining these two equations with the knowledge of theta t R1. Once you do that, we need to now, as we have seen earlier, we need to apply the end condition. The one end condition that will be of use to us is the torque to the right of this rotor, which is TR3. That TR3, that is going to be only 0. Well, the value corresponding to TR3 that you get is going to be the frequency equation. So TR3 equal to 0 leads us to a frequency equation. Actually, it will be in omega to the power 4, leading you to two values of omega 1 and omega 2, which are the two natural frequencies. Of course, this is a 3-rotor system, but there is no constraint at the end. Therefore, it's actually a 2 degree of freedom system, and it will lead to two natural frequencies. Here again, using these